All right, this is going to be the first part video for AP Statistics, Chapter 19 on confidence intervals for proportions. So this Unit 5, is really large. It contains chapters 18, 19, 20, 21, and 22. Chapter 18, we covered the idea of a sampling distribution, and we did that for both numerical data, where we could find means, and also categorical data, which is just yes or no, and we can find the percentage or proportion of yeses. To keep things more straightforward as we explore the other ideas in inferential statistics, for chapters 19, 20, 21, and 22, we're going to focus just on categorical data. And then in Unit 6, we'll talk about what we have to change to do the numerical part. Okay, so from here on out, we're talking about data which can only be expressed as a yes or no, so where we can find a percentage of yes. All right. And actually, usually we start this lesson with something called the eraser activity. So I'm going to try to describe this because it's something that we do with people in person. I'll describe what does happen here. Typically, what we do on the eraser activity is I ask for a volunteer in the classroom, and then I take that one student out in the hall and I explain kind of what's going to happen. Then when we come back in, I ask everybody except for this student to put their heads down on their desk so they can't see what's happening. And then I take my dry erase marker and I draw a little target on one of the whiteboards in the front of the room. And then I ask this selected student who volunteered to stand about 15 feet back from that. And then I give them a small pencil eraser and I ask them to try to throw it and make it hit the whiteboard as close as possible to the target. And I have them do that quite a few times. And then I have them take their seats, and then I erase the target mark. So only, I should have said that I mark with a dot every place where their eraser hits. So, but then I go back and erase the target that that person was aiming at, so that the class can only see the result of this person aiming at the target, but they don't get to see the target that they were aiming at. Okay. And I have everybody lift their head up and look, and then they see this on the board. So they see a bunch of dots that I've drawn, which are places where that person's eraser hit when they were aiming at a currently unknown target, right? All right, so then I ask another volunteer, somebody other than the person that threw the eraser, okay, come on up and draw a circle that you think contains where the target was if you had to be 90% sure that your circle does contain that target. And then I ask another person to come up and say, okay, what if we didn't have to be as sure, but I wanted to be more precise? Could you draw a circle that's maybe a little more accurate, but we'll only maybe be 70% sure that the target was in there? And usually people draw circles something like this. Like for the 90% circle, somebody draws a circle around all of the dots because we're pretty sure that the target is somewhere in the region where the dots are, right? But if we were allowed to be only 70% sure, then maybe we could draw a tighter circle because we're pretty sure, not 90% sure, but maybe 70% sure that the target's somewhere inside that smaller circle. Okay. And then I reveal where the target was, right? And so maybe the target was right here that was being aimed at, right? Maybe not. Okay. In fact, actually, the target isn't there. The target actually was over here where I've drawn it in red. So typically something like that. Okay. People will think the target's in the middle, and that's our best estimate of where the target was, is where that purple X is, because we have no reason to believe it wasn't right in the center. But often when we do this activity, the actual target was somewhere else, and the person just had kind of a little bit of a bias to what they were doing, and so they were always throwing down and to the right or something like that. Okay, so this red X is the actual target that the person was aiming at, and the purple dots are just what actually happened when we took a random sample of things. Okay. All right, so how does this help us figure out something called a confidence interval? Well, we're going to use this as sort of an analogy for how to analyze data. Okay, imagine that you had a population that you were trying to estimate something about, and it's categorical data. So you have some things defined as yes, and then you can calculate, well, if you knew the entire population, it has P, which is the parameter, the percentage of yeses in the entire population. And that's the target. That's the thing that we're actually trying to deal with, right? So that would represent this, right? This target is the population that we're trying to find, right? But we don't know that, right? In fact, we have to conduct an experiment or an observational study or something to collect some data. And we know that since that data is going to be sampled from the population, it's going to vary every time I do an experiment, right? So I take a sample of data, right? And in some way, I generate the percentage of yes in some sort of sample. That's like this x here, right? And so that would be a percentage for the sample, which we call p hat, because that's a statistic. Okay, so that's here. And these circles, these are what we call a confidence interval. We're going to go above and below what actually happened in our result, and we're that confident that the real value is somewhere inside that region. So maybe this small circle, we could represent it by going above and below this p hat value a certain amount, and say we're 70% confident that the target value p is inside there, right? But if we wanted to be more confident, then we have to have a much wider kind of confidence interval here to be more confident. In fact, if we wanted to be 100% confident, this would have to go out to infinity on each side, because the only way we could be 100% sure is if we went from negative infinity to infinity, right? So, okay, so the idea is that there's a trade-off here. There's a trade-off between precision, how narrow this is, and the confidence level, how confident we are that the real value is inside that region, okay? So this is the heart of inferential statistics. We're using something that happened in the sample to infer things about the population it came from. In this case, we have a value that we calculated from the sample, right? And by putting a boundary, an error boundary around it, then we can be a certain percent confident that the real target value for the population is inside there. And the way we're going to analyze this is that since this p hat follows a sampling distribution model, when we take p hats from, if we were to conduct this experiment many, many, many times, then the way this p hat moves around should follow our chapter 18 sampling distribution model for p hats, okay? All right, so that's kind of a background to what we're going to do. So let's actually look at a specific example, and we'll take a look at how this actually works and define terms more crisply. This example is from our textbook. One type of coral, which is called a sea fan, is threatened by a particular disease called aspergillosis. In in the year 2000, a team examined a sample of 104 sea fans off the coast of Mexico, and they found that 54 of the sea fans had this disease. The question we're going to want to answer is it possible to use that data to say anything about what percentage of all the sea fans in the world would have this disease? Okay, or at least all the sea fans in this region. All right, so this sample had a proportion that had the disease. It was 54 out of 104, so 51.9% of the sea fans had the disease in our sample. We would call that value p hat, and that's a statistic because it came from a sample, right? This isn't all the sea fans, it's just some of the sea fans. What we're trying to get at is the target value, which is the proportion of all the sea fans that have this disease. That would be called p, and that's a parameter. Okay, we know that our particular sample of 104 is just one of many possible samples of 104 sea fans that we could have taken. And if we had taken a different set, potentially we would have had different p hat value every time we did that. If we were to imagine taking all possible samples of 104 sea fans out of the population of sea fans, then the proportions would form the sampling distribution of sample proportions. It would have a shape as long as the conditions are met for sampling distributions, and it would have a mean, which would align itself with the true proportion of all, and then there would be a standard deviation, and we have a formula for that. It's the square root of pq over n, right? So we know how this p hat should vary from sample to sample. All right. Okay, so we have this particular sea fan, right? We know that that sampling distribution would be centered at the true proportion of all sea fans that have disease, but right now we do not know that value. So we have no idea whether our particular sample is on the low side or the high side, or maybe it's way on the high side. We have no idea where it is in relation to the true target value, okay? So what are we going to do? We do know, though, that we have a formula for finding the width of this, right? Regardless of where it is centered, we know that that width is going to be given by the square root of pq over n, okay? Unfortunately, we don't know this value, but we can approximate this by using the standard error, right? The standard error is the same formula, but we just use the p hat from our sample, and that's likely to be at least close, right? Okay. So let's put all these ideas together. We can't center our population or our sampling distribution at p because we don't know it, right? So instead what we do is we just we make the assumption that that shape will be the same. We're going to use the standard error version for standard deviation using our p hat value, but we're going to center everything not at p, but at the statistic. So whatever we actually got in our result, in this case our 51.9%, we're going to center our sampling distribution there instead. Okay, so what does that tell us? Well, that tells us that we should be able to figure out how likely the target value is to be a certain distance away from our statistic, right? When you center about it here, then you can use probability calculations for normal distribution to determine how likely it would be that our p-value would be a certain distance away or further. Okay, and if I want to be 70% confident of capturing that, then we know that if you go plus or minus 1 standard deviation, if you go from 1 standard deviation below to 1 standard deviation above, 68% of the data of a normal distribution is there. And so that means that if we want to be 70% confident that we have gone far enough out here to capture the real true target value, then we have to go just a little more than 1 standard deviation away on each side of our statistic, right? But on the other hand, if we wanted to be 90% confident, maybe we would have to go like 2 standard deviations away or 2.5 standard deviations away. All right. So we can adjust the width by deciding how many standard deviations to go above and below our statistic to set the boundaries of our what we call a confidence interval. Okay, and actually we'll start defining some terms here. The distance that we go on either side is called the margin of error. So whenever you see like a political poll that says that, Clinton's going to win with 52% plus or minus 3%, this plus or minus 3% is the margin of error, right? What percentage on either side are we putting a buffer in there because we're only a certain amount sure that the real value is in that region. All right, so let's put it all together here with some formal symbols. First of all, everything centers at the statistic, which is p hat. Okay, that p hat is called the statistic. Okay. So the next thing is we know that we can figure out the standard deviation, right? It would be the square root of pq over n, but because we have to use the p hat value instead of the p value because we don't know it, then it's called the standard error, okay? And so that's the standard deviation for this particular statistic. Since the statistic is a proportion, then it's going to be the square root of pq over n using the statistics value, okay? That's this part right here, okay? And then we're going to say, okay, what confidence level do I need? Depending on how confident I want to be, I'm going to choose a number of standard deviations to go above and below. Okay, so if I want to be 68% confident, I can go 1 standard deviation away, right? Let's see, if I went 2 standard deviations away, that's 95% of a normal distribution. So if we want to be 95% confident, we can go 2. Typically, we don't have to go just 1 or 2. We can go 1.4 or 1.69 or 2.19 or something like that. Okay, so the number of standard deviations we go above and below, that's a z-score because it's a number of standard deviations. So it's given the symbol z star, and it's called the critical value. So the critical value is how many of these standard deviations we're going to go. So if you take how big a standard deviation is, and then you multiply it by how many standard deviations away to go, then we're finding how far we're going on one side, okay? And that is called the margin of error. And we go both plus and minus that amount to form what's called the confidence interval. All right, so you can think of there being a formula for computing a confidence interval. The confidence interval, sometimes we abbreviate it CI, is the statistic, which in this case is p hat, plus or minus a number of standard deviations and times how big each of those standard deviations are. And then that will give you 2 values. Okay, we'll do an example here in a second. So how is it that we set this z star value? Well, that depends upon how confident we want to be. So there's another phrase. Confidence interval refers to the width of the interval itself. But there's another phrase called confidence level. And confidence level is how percentage confident we want to be that our interval captures the real value, that it's inside that interval. So for example, if we wanted to be 80% confident, then we could say on a normal distribution of z-scores, where mean is 0, standard deviation is 1, we would have 80% centered in the middle, and that would leave 20% left over, 10% here and 10% here. right? The way we find a boundary for that would be on a normal distribution to use inverse norm. So if you went inverse norm with 70% of the area below, or I'm sorry, 10% of the area below, and 0 is the mean and 1 is the standard deviation, you're going to get negative 1.28, which means you have to go 1.28 standard deviations below. So we just throw away the negative, and the z star value is that we have to go plus and minus 1.28 standard deviations. On the other hand, if we wanted to be 95% confident, then you'd have 95% in the middle. And that means 5% left over, 2.5% on the left and 2.5% on the right. So if you did inverse norm with 2.5% area to the left, then you have to go 1.96 standard deviations away, right? On either side. If you want to be 99% confident, you have to go 2.6 standard deviations away. If you want to be 90% confident, you only have to go 1.64 standard deviations away. So these numbers here are called the critical values for that match up with different percentage confidence levels. Okay, so for our CFAN problem, let's assume we want a confidence level of 95%. That's a very commonly used value. So if that's true, then we'll use a critical value of 1.96. That means that we will go plus and minus 1.96 of these standard deviations away. Okay, so then we can go ahead and compute this then. What we do is start by having our statistic, right? In fact, let me write the formula up here for a confidence interval. It's going to be the statistic p hat plus or minus the number of standard deviations we're moving away, which is z star, times how to calculate how big those standard deviations are. Okay, so the first thing we would want to know is the statistic. And so we would fill in our 0.519 here for the p hat. Okay, and then we would say plus or minus. Then we can calculate how big a standard deviation is, right? We don't know the p-value, so instead of square root of pq over n, we use the p hat. So that's 0.519. Q hat would be 1 minus that, the other 48.1%, and the sample size was 104. That means that this standard deviation would be 0.049, so that would go here, 0.049. And then the last thing we need to fill in is how many of those standard deviations do I want to go? So because I wanted to go, I wanted to have 95% confident, we're going to go 1.96 of those standard deviations away. So to finish the calculation, we would say 1.96 standard deviations that are each 0.049. Okay, so the next screen shows that being calculated, right? 0.519 plus or minus 1.96 standard deviations times the size of a standard deviation is 0.049. That means we're doing 0.519 plus or minus 0.096. So this 0.096 is the width that we're going to go plus and minus. So if you take 0.519 and subtract 0.096, you get the lower boundary here, which is 0.423. And then if you take 0.4519 and you add 0.096, you get the upper boundary, which is 0.615. Okay, and what that means is that we are 95% confident that somewhere between 42.3 and 61.5% of all the CFANs have this disease. Okay. That's the idea here, right? We'd like to know this value, but we don't know it, right? So we do an experiment to determine this value, which turned out to be 51.9%. So about 51.9% of the CFANs in our sample had the disease. But then we go through the calculation to figure out the confidence interval, which ended up being between 0.423 and 0.615. So now we can say, all right, we are 90, since we chose 95% confident, we're 95% confident that this value, which we don't know, is somewhere between 42.3% and 61.5%. All right, so that's how confidence intervals work. It's just take a statistic and add and subtract a margin of error. And the margin of error is some number of standard deviations. All right. So once you figure out how it works, it's really not too bad to calculate it, but it's weird to wrap your head around the first time you see it, right? We're taking what we know and we're inferring something about what we don't know yet about the entire population. So we can be 95% confident that for all CFANs, the percentage that have disease is somewhere between 42.3 and 61.5%. Right? And there's a trade-off, right? That's not very accurate, right? 42.3 to 61.5. If I wanted to narrow it down, Well, then I'd have to trade off confidence. If I drop this down to like 70%, then these numbers would get smaller and I'd be able to have a more narrow range, right? But I'd be less confident that that's actually true, that the real value is in that region. Okay. All right. So what does that 95% confidence really mean? Well, if you were to do this experiment many, many, many times with different CFANs, there's a thing here you can explore on this website called rossmanchance.com applets. I'm going to show that to you now here. Let's say that we had a proportion, and let's say that the real CFAN proportion here was 60% of the CFANs had the disease, right? And what I'm going to do is just take a single interval here and take a sample. Let's say we want to be 95% sure that we capture the value. So I take a sample. Some of them are yeses, they have the disease, some are no. And that means in this particular case, 56% of the CFANs had the disease. So on a number line here, there's a dot here at 0.56. And going through a 95% confidence interval calculation like we did, put this little bar here that we want plus or minus. And the reason why it's green is because the real value of 60% was captured by this, right? It was within that. If I take a different sample, then I'm going to get a different yeses and nos, different, this time 61% of the CFANs had the disease. So the p hat moved up here, and we have the same or similar calculation here, right? And I can keep doing that. Every time I take a different calculation, my little bar here, my confidence interval is centered at whatever p hat I got. So let's do 100 of them. If I do 100 of those, then every once in a while, I'm going to get a p hat value that's just randomly a little extra low or a little extra high, so low and so high, in fact, that the confidence interval calculated around it will no longer capture the real value. Right? So if you add this all up, right, 1, 2, 3, 4, 5, right, 5 of these 100 intervals did not capture the correct value of 60%, right? But 95% of the time, our confidence interval did capture that, right? So when people are asked to interpret what does 95% confident really mean, that confidence level of 95% means that if you were to repeat the experiment many, many, many times, then 95% of the times, since each confidence interval is centered around whatever happened in that particular trial, 95% of the times it would capture the real value for the population, but 5% of the time it wouldn't. Okay, so that's the meaning of 95% confidence. All right. And of course, there are calculator ways to do this. So let me actually show you how you can do this in a calculator. What we're going to do in this first unit is sometimes I'm going to ask you to do these calculations by hand like we did over here. And sometimes I'm going to ask you to do them in a calculator. Okay. So right off at the beginning, I'm going to show you both ways, but you need to be prepared to do it either way, either by hand or using a calculator. So if you have a TI-83 or an 84, it has lots of statistical, what we call tests built in. So if you go to the stat button and then you slide past calculations over here to tests, then we're going to see that this is called a one proportion Z interval. Okay. The interval means we're calculating a confidence interval. The Z means we're using Z scores, which are true for proportions. This is about a single proportion. In other words, our data has just a single sample where we can calculate one p hat value. Right. So if I scroll down here, it's pretty far down. There's one of these tests that's called one prop Z int. So if you select that, it'll bring up a little screen here. And for the X, what we have to do is put the number of yeses that we had in our experiment. So in this experiment, we got 54 CFANs that had the disease. And then for the N, we put the total number that were in the sample, which was 104 CFANs. And then for C level, we put the confidence level. So if I want 95% confidence, I put 0.95. Okay, and then we say calculate. And what it'll do is give me the boundaries, 0.423 to 0.615. So it just does the calculation for us. Sometimes we'll allow you to use that. Other times we'll ask you to do it by hand. So when you practice, you should probably practice it by hand and then use the calculator function to check to see if you got the right answer. All right. All right, so a couple other things before we wrap up for the day and maybe look at one other example. So there are some problems that we'll see more of tomorrow But there are some problems where we don't know the value for p hat, or we want to assume a value. So if you're trying to come up with the worst case margin of error that would guarantee to work no matter what p hat is, then you would want p hat to be whatever would give us the biggest standard error. So the biggest standard error, since it's p hat q hat over n, is if you make p hat equal to 0.5, then this ends up being 0.5 times 0.5 over n, right? And any other p hat, so if you had, like, say, a p hat that was 0.6 and this was 0.4, that will always be a little bit less than this. So if you want like a worst case margin of error, you want to be guaranteed that you have a certain percentage chance. What you can do in certain circumstances is just use 0.5 as the default value, because that will always give us the widest possible interval that guarantees that we're capturing that value. All right. Okay, everything here is based on assumptions and conditions, mainly because it's assuming that we have a normal shape for that distribution of p hats. So here are the official conditions that we have to check before we do any confidence interval problem. First of all, there's some assumptions and then corresponding conditions that go with them. I just think of them the same thing. Our book makes this big difference between the assumptions and then the conditions that show the assumptions are true. But in my mind, they're this kind of the same thing. So we have to be able to assume that everything is independent, that in the CFAN example, that one CFAN having the disease means that the other ones may or may not, but one having it doesn't affect whether the next one in the sample has it, right? So we want to have what's called the randomization condition. And that typically is that we have taken a random sample of the population. We usually express this as SRS. In other words, the sample has to be a simple random sample, or we have to believe otherwise that it's representative of the population, right? We have to also meet the 10% condition. We want, if we're sampling without replacement, which we typically are, we don't want to sample more than 10% of the population. That's always true for a variety of reasons, right? So it's basically the same conditions we had in chapter 18 for proportions. We want to make sure that the elements in the sample are not affecting each other. So we need to be able to assume that they're independent. And then although we don't want the sample to be too big and go over 10%, it does have to be big enough to make sure this is normal. And since proportions are based on binomial, we have to have NP and NQ be at least 10, right? So there's basically SRS, 10%, less than 10% sampled, but at least enough to get NP and NQ at least 10. And we want to believe that the samples are independent from each other. All right, so let's do another one. This is another example problem. In May 2002, the Gallup poll asked 537 randomly selected U.S. adults this question. Generally speaking, do you believe the death penalty is applied fairly or unfairly in the country today? And the only choices they were given is yes or no. So of these, 53% of the people answered fairly. What can we conclude about the proportion of all U.S. who would respond the same way? Okay, so here's what I'm going to do. I'm going to group this and shrink it down a little bit, and then we'll just go ahead and work this together right here on this page. All right. First of all, if you want to think about kind of a procedure, you can say identify the population, the parameter you wish to estimate, and we'll select a confidence level if it's not provided. So what we're talking about here, the population is all U.S. adults. Okay, and the sample is N equals 537 adults that were asked the question. So there was a randomly selected sample of 537 that we're estimating. What is it that we're trying to find? Well, at the population, we want P, and at the sample, we have P hat. What P and P hat are the percentage of people who say yes to this question. Okay. All right. So what do I have right now? Well, I have 53%. That came from the sample. So that means that my p hat is 0.53. 53% of the people said that. I'm trying to figure out what the corresponding p is in the whole population. Okay, and this didn't really tell me a confidence level, so I get to choose this. So for the confidence level, we're going to choose that we want to be 95% confident in the results. That's going to determine how wide we have to go. Okay, the next thing we would do is verify the conditions. So what are the conditions? Well, first of all, we have to believe that we have an SRS and we have independence, right? This, I'm going to say that the problem said, I'll cite the wording randomly selected as the reason why I believe this is true. Because if you randomly selected people, they're likely to be representative and they're likely to not be connected in any way. Okay. Another thing is we have to have N be less than 10% of the population, right? So in this case, 537 is definitely less than 10% of all US adults. So I will write that out as my justification for why I believe that is met. So we're checking conditions here. Okay, and then the next thing we would do is we'd want to say that NP and NQ have to both be greater than or equal to 10. So N is 537 and P is 0.53. Right now I'm going to use, I don't have P, right? Because I'm trying to find that. So I'm going to use my P hat because that's the only thing I do have for calculating this. 537 times 0.53. So when you don't have P, you use the P hat instead. This is 284.6, and then 537 times the other 47%. So if I take that times 537, that is 252. So 252.4. So both of these are greater than 10. So all of this means that it's legal to use a confidence interval calculation because it's based on a normal distribution. Since the conditions are met, now we'll go ahead and calculate. So here's what I would do. I would write out the formula. Confidence interval is p hat plus or minus z star times the square root of p hat q hat over n. Okay, for the z star, that's going to depend on the confidence level. So let's do a calculation over here based on the fact that we're choosing to be 95% confident. So we'll draw a little z-score distribution. We'll say, all right, I want to be 95% confident in the middle, which means there's 5% left over, 2.5% of it's there, 2.5% of it's there, and I'm going to say, all right, what is this boundary value here? So the z star we can find with inverse norm. It would be 0.025 to the left on 0 and 1 for the mean and standard deviation. And so you would go to your calculator and go to second variables down here to inverse norm, 0.025, and then 0, 1. That is going to be negative 1.96, but I'm going to throw away the negative. So I need my z star value to be 1.96. So let me go ahead and fill that in, 1.96. Okay, I also have my p hat value. It's 0.53, so I'll fill that in, 0.53. Okay, and then the last part to fill in is the standard deviations calculation. So that's going to be the square root of the p hat is 0.53, right? The q is the other 47%, and the sample size in this case is 537. So if you compute that all out, the square root of 0.53 times 0.47 divided by 537 turns out to be about 0.0215. And then I've got my 1.96 here and my 0.53. Okay. Let me multiply these two numbers. I'm taking the unrounded version times 1.96. This actually ends up being then 0.53 plus or minus, and we're going to multiply these two things together and get 0.0422. This is called the margin of error here, how much we're going to go above and below. So that means that my final answer is going to be, I usually use interval notation, so we'll put a kind of a brace here, and we'll take 0.53 and subtract that number. So 0.53 minus 0.0422 is 0.4878. And the maximum number will be 0.53 plus. So 0.53 plus 0.0422 is 0.5722. Okay. And then finally, we want to state the result in the context of the problem. So there's a standardized sentence we want to write for this. Okay, let me write it down here. We're going to say, we are 95% confident. We'll always indicate our confidence level that the true percentage of all US adults who would say yes is between, and then we'll put our numbers here, 48.8% and 57.2%. Okay, so that's called interpreting the confidence interval, and we're always required to write that sentence after we've computed it. Okay, the last thing we might do is just check this in our calculator to make sure there wasn't a mistake in our calculation. So we have even though I'm going to require you to show this work, you can double check it by going stat, tests, and then down to one prop z test, or sorry, z interval. This time we had, okay, now here's the thing, right? We were given a percentage, 53%, right, of this, but the calculator requires that we enter a count, not a percentage. So let me get back out of here, right? What is 53% of 537? Well, that's 284.6, right? So what we're going to enter for that, let me go back into that again for the one prop z interval. Okay, we're going to have to, this must be a count, so it has to be rounded to an integer. So the closest we can get instant for 284.6 is to enter 285. So it's going to be 285 out of the 537. And we decided to go with 0.95, 95% confidence. And this calculated 0.488 to 0.573. Within 3 decimal points, this is exactly what we got. Okay. By the way, this p hat down here, this is the 53% that we were given in the problem. It just recalculates that. All right, so this is the way we would do a problem. And that's pretty much it. There's some offshoot things that we're going to talk about in the next lesson, but this right here is the heart of what we're doing. Let's see. Yeah. One last thing before we wrap up this first part video. What can you do to change the confidence level? So confidence is p hat plus or minus z star times the square root of pq over n. Okay. What if you want to, if you select the confidence level, right? So the confidence level, that affects the z star value, right? If you make your confidence go down, like let's say from 90% down to 70%, right, then that means you don't have to go as many standard deviations away, which means the z star value goes down. If the z star value goes down, then the whole margin of error goes down, and therefore the width of the whole thing goes down. So if you need to have a more precise result, like you don't want to go from 20% to 80%, what you want to be able to say something like 48% to 52%, then you either have to lower your confidence level, or the other thing you can do is you can increase your sample size. Because if you increase your sample size, then because it's on the bottom here, this will go down. And if that goes down, that also drives the margin of error down, which also reduces the width. So the two ways to make a narrower confidence interval is to decrease the confidence level or to increase the sample size. All right. And that's where we're going to leave it for the first part.